Hello AAF kids, welcome to Triangle Trig Review. But first we're going to do a warm-up with our angles and arcs. Notice that the angles written in red and the arc is written in blue. So for an angle, I didn't ask you to, but I could ask you to sketch it. 225, remember, if I'm doing an angle, I'm going to spin from standard position around to quadrant 3, showing positive direction, and that's 225 degrees. And its reference angle is measured back up to back up to the horizontal, so its reference angle is 225 degrees minus 180 degrees, which is of course 45 degrees. Hopefully you didn't actually have to do that. Right, math? 330, spinning around here to the fourth quadrant, showing the ray going from the center to the circumference. That's 330 degrees. Measure the reference angle, measured to the closest horizontal is how far away? Okay, 330 up to 360 would be 30 degrees. Negative 150, negative 90, negative 90, negative 150. It's a terrible drawing. Negative 150 degrees. Of course, going 30 more degrees gets me to the closest horizontal. Remember, reference angles are always positive. 630, what is that, right? Well, that's certainly more than 360. There's one 360, two 360s, 720, and this is how many 360s? Whee! Not actually. 630 degrees. So its reference angle, remember, I landed on a boundary. Oh, whoops, my bad, I was doing the next one. 630 is not three 360s, that's right, 630. There is 360. 360. Now how much more? If I right, how much more do I have? 360. It's 270, right? So I'm going to go all the way around here. There's 630, but since that's a boundary, there is no reference angle, right? No reference angle if you're a boundary. 1080, that's the one that is 360 and 360 is 720, plus another 360 is 1080. So that one is the one that is 1, 2, 3. Also no reference angle since you landed on a boundary. This one landed on the negative y-axis. This one landed on the positive negative y-axis, positive x-axis. How about 230? Where the heck is that? Well, 230 is certainly more than 180, but not as quite as much as 270. Right? But how far is that from the closest horizontal, right? I need to do 230 degrees minus 180. What is that? 50 degrees, right? So the reference angle is 50 degrees. This is not one of our special angles, is it? Boundaries are special, right? Boundaries are specials. 30, 60, 90. Or any multiples, 30, 60, 90, 45s, or multiples of those are special. Now let's talk about our arcs. Now remember, an arc is going to be in the same, right? It's the same, we're just talking in a different language, but if this is 225 degrees, the arc is measured along the circumference, but to the same place. That arc is 225. 225, remember the reference angle was 45 degrees. How many 45s was this? This was 1/4 of pi, 2/4 of pi, 3/4 of pi, 4/4 of pi, and 5/4 of pi. Right? One more pi over 4 than 180. Reference arcs are awesome. Right? The reference arc is just going to be pi over 4. How about 330? 330 has a reference angle of 30 degrees. So what does that mean? That means going all the way around the circumference. I'm 1 pi over 6 short of being all the way to 2 pi. Well, how many sixths of pi is all the way around? That's right, 12. So this is 11 pi over 6s. What's the reference arc? Hello, pi over 6. Right? I love reference arcs. Negative 150. Negative 150 is also going to have a negative arc then, right? But its reference angle is 30 degrees. It's not quite to negative 6/6 pi. Yeah, you can go ahead, huh? Right? Negative 1/6, negative 2/6, negative 3/6, negative 4/6, negative 5/6. Negative 5/6 pi. How much is left to get to the closest horizontal? Pi over 6. 630 degrees, what is that? If that lands on the negative y-axis, right, it was around the circumference once, 2 pi. 2 pi, remember, if I'm going to a y-axis, I want to be in halves. So 2 pi is how many, right? 4 halves pi, 5 halves pi, 6 halves pi, 7 halves pi. Seven pi over 2s, right? 7. Reference arc, again, if you're on a boundary, there is none. Ten 8, this is also not going to have, right? This is still going to be the same. Going around once the circumference was 2 pi, 4 pi, and then what? 6 pi. Since this one is not special, I'm going to use my formula. If I want radians, radians is equal to the degrees I have times pi over 180 degrees. If you're dividing degrees by degrees, the degrees cancel out, the zeros will cancel out, and this is 23 pi over 18. Now I can't do my little trick, right? This is not a special angle. I can't say the reference arc is pi over 18. So I have to go over here and I have to think. Let's go over to my circle and think. I am going to go around to the same place, right? This is going to be 23 over 18 pi. Well, don't you agree that this over here must be 18 over 18 pi, right? Isn't this just 1 pi going around the half circle? 1 pi? Well, if this is 18 over 18 pi, and this is 23 over 18 pi, what's the reference arc? You had to go 5 more 18ths to get to 23 18ths, right? Kind of cool. Alright. We're going to leave the circle for a little bit, and we're going to do a little geometry review, but the geometry review is going to be trigonometry with your triangle. So remember, for any triangle, and I don't know why I kept forgetting to put the right angle measure in here. This is a right triangle. If I tell you that right triangle is ABC, and I focus you on angle A. First I have to focus you on an angle. There's angle A. If I reference angle A, then the side touching angle A, that is not the hypotenuse, because obviously the hypotenuse here is also touching angle A, right? But the side that is not the hypotenuse is called adjacent, and the side across from angle A is called the opposite, and the longest side, which is always across from the biggest angle, which in a right triangle is 90 degrees, is called the hypotenuse. Making a ratio, I can make a ratio of 1 to 2, I can make a ratio of 7 to 5, I can make a ratio of smiley faces to frowny faces. I can make any ratio I want by putting one thing on top of another. Trigonometric ratios come from a triangle, and the trigonometric ratios are tangent, abbreviated as tan, sine, please do not call this sin, this is sine. I don't know why they couldn't bother to write the E. Please do not call this cos. This is cosine, right? So these are the ratios. Tangent doesn't look like a ratio until I define it. The ratio, the tangent of any angle, right? And we're Greek letters, theta. The tangent of any angle is a ratio of the opposite side of a triangle compared to the adjacent. The sine of any angle of a right triangle is the opposite compared to the hypotenuse, and the cosine of any angle is the adjacent compared to the hypotenuse. Notice that sine and cosine both have the hypotenuse in it, and tangent as a denominator, and tangent does not. Tangent's the only ratio that does not have the hypotenuse out of sine, cosine, and tangent. These ratios are the same no matter what size your right triangle is, right? I don't care what size it is. I can make a ratio of the sides. There was an American Indian princess who was one of the first ones to draw these out and kind of give them names, and her name was Sakatoa, and it was amazing because Sakatoa kind of goes with S, right? Sine is the opposite over the hypotenuse. Cosine is the adjacent side over the hypotenuse, and tangent is the opposite over the hypotenuse. No, I'm just kidding. I mean, I'm not kidding about Sakatoga. I'm kidding that that is an American Indian princess. But just makes me think of that. But I have to tell you and be honest that when I was in school, we didn't learn Sakatoa. When somebody first told me that when I started teaching, I thought they were talking about sucking toes or something. But all I learned was Oscar has a heap of apples. So I never learned that was my mnemonic device. Oscar has a heap of apples. Okay. Sine, cosine, tangent. Again, remember that sine and cosine have the hypotenuse in it. Now let me ask you a question. When I have a right triangle, this is a 90-degree angle. These two angles must be smaller than 90 degrees, right? Otherwise the triangle wouldn't have, right, for a triangle to have 180 degrees. And the longest side of a triangle is always opposite the 90-degree angle. So, if I'm talking about the opposite, if I again call this angle A, the opposite side here, this side has to be smaller than the hypotenuse. Think about a ratio. If you're comparing an opposite side to a hypotenuse which must be longer, what is true about a fraction whose numerator is smaller than its denominator? That's right, this ratio must be less than and will never be equal to 1 in a right triangle. You can say the same thing for a cosine, right? The adjacent side of a triangle is always smaller than the hypotenuse of a right triangle. So in a triangle, the cosine of any angle will always be less than 1. Can't say the same for tangent, right? Because tangent is just a ratio of two sides, and who knows whether the opposite or the adjacent side. So tangent may be bigger than 1, may be smaller than 1, could also be 1. What do you think? Could the two sides of a right triangle ever be equal? Sure, right? 45, 45. 90 triangle, right? Well, Sakatoa has a cousin named Shashakawa. And this is for the reciprocal trig ratios. So, these relationships are just the reciprocals of the original trig ratios. Cosecant is the reciprocal of sine, so instead of the opposite over hypotenuse, it is the reciprocal. Secant is the reciprocal of cosine, and cotangent is the reciprocal of tangent. This is cosecant, which is the reciprocal of sine. This is secant, and wouldn't it be nice if cosecant was the reciprocal of cosine? So annoying, right? Yes, there is a reason. Secant is the reciprocal of cosine, and cotangent is the reciprocal of tangent. That makes more sense. So let me ask you the same question. If the hypotenuse is the largest side of a right triangle, and what is true about any fraction whose numerator is bigger than its denominator? That's right, this will always be greater than 1. So will secant. And cotangent, same issue. Don't know whether that's smaller than 1, less than 1, or equal to 1, right? So let's go back to this triangle. Given the right triangle, and focusing you on an angle L, so that's this one, what is the sine of angle L? Sine is the opposite side over the hypotenuse, so that would be 8 centimeters. over 10 centimeters. Centimeters cross out, and this of course reduces to what? Right? Cosine is the adjacent side compared to the hypotenuse, which is 6 centimeters over 10 centimeters. Centimeters divided by centimeters cancels out, and this of course reduces to what? No units. The units canceled out. The tangent is the opposite side compared to the adjacent side. The opposite side is 8 centimeters compared to the adjacent side, which is 6 centimeters. Centimeters divided by centimeters cancels one another out, and this ratio is 4/3. Notice that sine is less than 1, 4/5 is less than 1, cosine 3/5 less than 1. Tangent in this case, because the opposite side was longer than the adjacent side, in this case tangent was greater than 1. Now let's do the reciprocals. What are the reciprocals? The reciprocal of sine is cosecant. So the cosecant of angle L isn't 4/5, it's 5/4, which of course is greater than 1. The reciprocal of cosine is called secant, and that is not 3/5, but it is, which is greater than 1. And tangent of angle L is the adjacent over the hypotenuse, which is smaller than 1. Okay? So nothing more than just listing them. What are the trig ratios given a triangle? Give them to me. Don't need any meaning yet. So let's look at this one. If I tell you that the sine of angle L is 1/3, sine, remember, goes with the opposite over the hypotenuse. So I could tell you that this was 3 units, and this was 1 unit. Right? I don't know what the units were because they canceled out when they made a ratio, right? But isn't this true that this is the opposite over hypotenuse? Well, what's cosine then? I know that cosine is the adjacent side over the hypotenuse, so that's got to be something over 3. And I know tangent is the opposite over adjacent, so that's 1 over, I don't know. Hello, someone's at the door. Hello. Oh, come in, Pythagoras. Right? If you have 2 sides of a right triangle, can't you find the third? The hypotenuse squared is equal to 1 of the legs squared plus the other leg squared. 9 minus 1 is usually 8. I don't need plus and minus square root of 8 because I am talking about the length of a triangle. So my unknown side is the square root of 8. Right? So that means is it 1/3 is certainly less than 1. What's the square root of 8? Square root of 8 is bigger than 2, but is it bigger than 3? Nope, so this is less than 1, and in this case the tangent is also less than 1. Could you do the reciprocals? Right, the reciprocal cosecant would be 3 over 1, or just 3. Secant of L would be 3 over root 8, and cotangent of L would be root 8 over 1. Alright, how about this one? So this one has, same again, right triangle. Sine of angle L is the opposite y centimeters over the hypotenuse 1 centimeter. Centimeters cross out, and y over 1 is just y. How about the cosine? X centimeters over the hypotenuse 1 centimeter. Centimeters over centimeters cancel out. X. Tangent is opposite over adjacent. Cancel, cancel. Tangent is y compared to x. Just a minute here. Hey. See my face here? Where have I seen y over x before? Horizontal compared to vertical. No. Vertical compared to horizontal as a ratio. What have you seen with that before? I can't think of it right now. I'll get back to it. Oh, can you do the reciprocals? What is the cosecant of angle L? It's not y, it's 1 over y. How about the secant of L? Well, it's not x, it's 1 over x. And how about cotangent? It's not y over x, it's x over y. Alright, that's it for now. You can pick up the handout on your way out from the substitute. It has a practice with like the warm-up doing angles and reference angles and some arcs. And I will check all homework handouts from Thursday and Friday on Monday. Have a great weekend.